Hello, in this video I'll go over the simple gear trains assignment and demonstrate how you can do motion linking with a set of gears. Here we have the simple gear trains assignment, in which you can see is attached several gears in different teeth ranges, right? These increase in size as they increase in the number of teeth. Those are directly proportional. And there are two 12 teeth gears, one labeled a drive gear that is painted green. It should always be the input gear in the system. These gears come from the Vex Robotics website, where they have robotics parts. These are the parts we use within the engineering pathway, and all of these parts have downloadable CAD files right here, which you can go to. And so these are just the basic gears, 36, 12, 84, and 60. But in the future, if you would like to, you can download a variety of other types of gears, worm gears, rack gear and pinion, so forth. And so this is a valuable resource to have available to you. And so you can design whole robots with, if you would like to, out of these parts within Fusion. This is a look at the assignment, in which you have 4 problems labeled here. And these are to build simple gear trains. Simple gear trains are gear trains where each gear touches one right after the other, and you can think of them as in comparison to compound gear trains, in which you have more than one gear sharing an axle. And so here we'll only have one gear per axle, and that is our simple gear trains. And so we could have more than one output if we would like on these. The first couple problems we have just one output. And so what does that mean? Let's look at an example. Here we can see a set of the gears here. And for the purposes of this example, what we mean by output gear is one that is not in the middle of other gears. And so this set of gears has 2 outputs, this one on top and this one at the end, and then the green one is the input gear in that case. Next is the gear ratio. This is a formula that's found here. I put it in this document so you can read it. So the gear ratio is the number of teeth on the output gear divided by the number of teeth on the input gear. And that is a force multiplier, which increases the torque. That's the rotational force, right? But it also decreases the speed by the inverse of whatever the gear ratio is. And so if you flip this fraction around, let's say, and instead divide the number of teeth on the input gear by the number on the output gear, you would get the difference in speed between them. And so here we have different gear ratios corresponding to the gears, with a 1 ratio representing a output gear with 12 teeth and an input gear with 12 teeth. You might have more gears, as you will definitely need for the second problem, in which both gears need to spin the same direction. You'll have to add a gear in the middle. That'll be your idler gear. Then you also have other combinations with gear ratios of 3 and 5 on the outputs, and then 5 and 7 on the outputs, with the direction they spin changing. And so you have to think about how to place or add additional gears to create the output spin direction that you would like, or that you need for the problem. So here I've got an example where I'll show you how to do the motion linking. I've also got a gear spacing formula with the information you need for precise gear spacing. So I start by dragging in the input gear to that. I'll just press OK. Well, first you should unground it from the parent. You uncheck this box here where it says ground to parent. That's going to be important to allow it to move later. I'll press OK. If you've forgotten to do that, you can also find that option up here and by right-clicking on that component. Next, I'll drag in another gear, the 36-tooth gear. And for this one, I'm going to need to shift it to the right. And I can do that, or if I wanted to the left, I would just make this negative, but I'm going to use this X distance along with the formula here to shift it the proper amount. And so I'm just going to type in the numbers from my formula. Let's see. So it's the teeth on number 1, which was 12, plus the teeth on number 2, which is 36. And then that's going to be divided by 2 times the diametrical pitch, which is 24 for Vex gears. And then I can press enter, and the gears are properly spaced. Now I will make them rotate by going to the Assemble menu and choose As Built Joint. Then I'll click on my first gear. Then I'll click up on the top level component where it says Motion Link Demo. This is the name of my file. Yeah, top level component. And then I need a snap. And so I'll hover over the circular face of the gear and then hold the Control key on the keyboard. And I will click on that center point. By holding the Control key, it keeps it there. If I were to let it go, it disappears. So I want to be able to make sure I have that. And now it's rotating, so I'm going to press OK. I'll do the same thing for the other one. So Assemble, As Built Joint, click on this gear, on the Motion Link Demo. Now you might have it say that it's rigid. It might default to rigid like this, in which case you would have to switch it using your menu to Revolute. And then, of course, choose the snap. So I'll hover, hold Control, and then get that center point to begin rotating it. And so now both gears have the ability to rotate. They just do not rotate together. So I'm going to go ahead and at this point position these gears kind of close, so maybe that they're touching partially right about here before beginning to set the motion link. To do the motion link, I'm going to go up to Assemble again, and then in the menu here we have Motion Link. I click on that. Now it's saying that the component positions have changed. I want to just keep them where they're at, so I'm going to click Capture Position. And then it wants to know what joints do I want to link the motions of, and that. So I'll click my 2 joints, one and the other. But now the gears, they're rotating the same direction. These should be rotating in opposite directions. And so I'm going to click this reverse checkbox over here. And then now there's both spinning, and they're both spinning at the same speed, because in the text, the option box here, it's saying that when one joint rotates 360 degrees, the other one will too. But we know from the use of our formula that the other one should spin the larger one, the output gear, should spin at 1/3 of the speed of the input gear. There's different ways to do this in the box. Probably the easiest would be to take our gear ratio, which was 3, and just multiply it by this number by that. And so we can do 3 times that, and it will work, right? So now they are spinning at the same speed relative to each other. We could confirm that by starting to rotate them and see that they are meshing together just right. That is how you do the motion link. Next, after you get done with all 4 problems, which should be in the same file, you'll just build one under the other. Next, after that, you will want to do a motion study. And so the motion study is in the Assemble menu here under Motion Link. And with the motion study, you'll have to click on the joints to animate. And so for your 4 problems, you can get all 4 of them doing this if you have multiple ones. I'm just going to do one here. But each time you click on one, you'll get this timeline, this sort of frame points. And all you have to do is click on the very last one at 100 here. And then we're going to type in the angle that it should be at that point. And let's say 360 degrees. And then I'm going to click the loop here. I want it to play in a loop. And then click the play button. And you can see it'll loop around here just like this. And this is what you'll record by pressing the print screen button or using the print screen option, and then switch it over to video and have them all playing at the same time. We can also adjust the speed on that if it seems a little bit too fast. You see this might be more viewable. So that is how you do Motion Link and the motion study features using Fusion to create your simple gear train.